Hello, today we will be going over the two-pointer pattern. Two pointers are typically used when you are asked to find a matching combination and the array is sorted. So let's jump into an example. Okay, so here's a question for today. Given an array of sorted numbers and a target sum, find a pair in the array whose sum is equal to the given target. Write a function to return the indices of the two numbers, i.e. the pair, such that they add up to the given target. Here's our example. Input is an array of 1, 2, 3, 4, 6, and our target is 6. The output for this would be 1 and 3, because the numbers at index 1 and 3, being number 2 and 4, add up to 6. So first, let's go over this problem with a brute force solution, being a nested loop. So here on the left, I have just a sequence of how the pattern will work. On the middle, I have a rough sketch of the code itself. And then on the right, I will have a live view of how the pattern is moving. So the way this approach works is that we start our first for loop, I equals 0, and we're trying to count all the numbers. And then inside of that, we have a second for loop, which is j equals I plus 1. The reason why it's I plus 1 is because we always want to start to the number next to I. So that way we never find a duplicate pair. It's always going to be unique index. From there, every single time we have a new I and j, we will do this if. If nums I plus nums j equals target, then we return I and j. If not, we continue looping. So now let's run through a few examples. Here we have I equals 0, j equals I plus 1, which is 0 plus 1, which is 1, and we have 1 and 2. 1 plus 2 does not equal 6, so we move forward. Now j is index 2, and I still stays on 0 because this for loop in here iterates every single value after I until the end, and then we move I. So with that in mind, now we have 1 and 3 equals 4, not 6, so we move forward. Again, I stays where it is. J is now the number 4. 1 plus 4 equals 5. That is not equal 6. So we move again. 1 plus 6 equals 7. That is not 6. At this point, J has reached num's length. There are no more numbers, so we have to move I. So we reset. Now I equals 1. J equals I plus 1, which is now 1 plus 1 equals 2. So at index 2 and index 1, we will keep going. 2 plus 3 does not equal 6. So we move forward. And here, 6 steps later, 2 plus 4 does equal 6. So now that we have found a sum that equals target, we can return index 1 and 3, since index 1 and 3 do equal 6. But let's imagine now, how many steps would it require for us to find a target of 10 with this array? Well, it would actually take us 10 steps just for that simple change. It may not be easy to see how fast the number of steps goes up depending on the target and the size of the array, but for this sort of solution, for this nested approach, it can go up pretty fast. The time complexity for this solution is O(n) squared. The reason being is that for each number that you're checking for I, you then check all of the other numbers in the array. Once you reach the end with j, which would be the entirety of num's length, then finally you move I 1. Then you start over with j from I plus 1 for j, and then go all the way down until the end of nums, and then move I again, reinitiate j, and same thing goes every single time. That checking every single number after I is what makes this a rather slow solution. Space-wise, we're okay, O of 1 constant, because we are not storing any new values or anything, so that is good. So now the question is, can we reduce time down to at least O of n linear time? Well, with two pointers, we can. So the difference here is that instead of having I and j or 2 at the beginning of the array, we will now initiate a left pointer at the beginning of the array and a right pointer at the end of the array. We still have a sorted array, so now we can confidently say that with a sorted array, the left pointer will always be pointing to a lower number, and the right pointer will always be pointing at a larger number. The reason why we have this while left is less than right is because if we have left here at the beginning and right at the end, if they both reach 3, and 3 plus 3 does equal the target of 6, that would be a valid sum, but we need unique indices for this pair. So we can't return an output of 2 and 2. They can't be pointing to the same index. That is why we have this check right here. So let's go through a few steps of this so you can see how it works. We first have our current sum of nums left plus nums right, followed by a check. Does current sum equal target? 1 plus 6 equals 7. Does 7 equal 6? No, it does not. So now we go to our second check, which will determine which side we move and will help us dial in our solution. So is 6 greater than 7? No, it is not. So we have to move right down. Since our current sum is larger than target and we have a sorted array, we can confidently say that we need to move down to ideally find a closer solution. If we were to move left up, we would only be increasing current sum and never get closer to target, because then you would have 2 plus 6, 8, 3 plus 6, 9, 4 plus 6, 10. You never got closer to 6. All right, so let's go to the next step. All right, now current sum is nums left, nums right. 1 plus 4 equals 5. Does 5 equal 6? No, it does not. And now here's the check. 6 is greater than 5. We want to move left up and see how that kind of balances itself out. That's the movement that we're trying to dial in to the right pair. So now the next check. Current sum now equals 6. So when we do this if condition, does 6 equal 6? Yes, it does. So now we can return the index of 1 and 3, 2 and 4. So with that, we were able to reduce the time down to O of n linear and keep space O of 1 constant, which is great. So now, as a recap, when would you want to use the 2 pointers? When you're dealing with a sorted array or linked list and you need to find a set of elements that fulfill certain constraints. So in this case, find a matching pair of unique indices. And lastly, here are some other problems that you can also use 2 pointers with. And again, the 2-pointer pattern or these patterns that I'm in this series aren't necessarily the best, the most optimized way of solving these problems, but they do give you a framework for how to handle new problems that might initially seem completely new, that have no semblance of anything that you've done in the past. These patterns are just trying to get you to be aware of certain keywords and certain aspects of a problem to identify the correct data structure or a correct data structure and a correct way of working through the problem. So there's nothing wrong if you're currently just working with brute force solutions. Just try to work up to these and just have these in your toolkit. So with that, thank you very much for watching. Leave a comment down below or any questions that you may have. Please subscribe and I'll see you next time. Bye.